In this video, I'm going to talk about the ratio test and then I'm going to show you how to prove the ratio test. So let's consider this series, summation n is equal to 0 to infinity, absolute value of a sub n, and consider the limit n approaches infinity, absolute value of a sub n plus 1 over a sub n, and let's assume it to be rho. Now, this is the Greek letter rho, R-H-O. So there are three scenarios. Scenario number 1, if rho is less than 1, then the series will converge absolutely. If rho is greater than 1 or infinity, then the series will diverge. On the other hand, if rho is 1, then you cannot make any conclusion. The series could either converge or diverge. Now, I'm going to prove you these three cases one by one. So let's consider the first one, which is the most difficult one, and the other two are quite easy actually. So case number 1. So case 1, where rho is less than 1. Now, this limit approach is equal to rho. So for some number n, okay, so this little subscript n, if it is greater than or equal to some capital N, it is always possible to take this ratio arbitrarily close to rho. That's what it means, that it approaches rho, which is equivalent to saying that the difference between this ratio and rho could be made arbitrarily small. If we put it mathematically, this is what it means. Absolute value of the whole thing, absolute value of a sub n plus 1 divided by a sub n minus rho, absolute value must be less than epsilon, where epsilon is some positive number. Epsilon is arbitrary, greater than 0. That means we could make it as small as we want, okay? Now, what I'm going to do, I'm going to take this term on the left-hand side and I'm going to break it down into two pieces. You will see what I'm doing here. So, absolute value of a sub n plus 1 divided by a sub n, capital N of course, minus absolute value of rho, which is positive, so I'm going to just put rho, is less than or equal to this guy, which means absolute value of a sub n plus 1 over a sub n, okay, minus rho, absolute value, which is less than epsilon. Remember, here I use this property, okay, a minus b, absolute value of it is greater than or equal to absolute value of a minus absolute value of b. But I used it in the reverse order, or just said absolute value of a minus absolute value of b is less than or equal to absolute value of a minus b. That's what I used. Now, I'm going to take this and compare it with that. If I do that, I'm going to get absolute value of a sub n plus 1 divided by absolute value of a sub n, okay? Then I move the rho to the right, must be less than rho plus epsilon. Now, please note that rho plus epsilon must be less than 1 because we can make the epsilon as small as we want. So rho plus epsilon could be made to be less than 1 for so long this capital N is big enough. So let me just try to explain it to you what I mean. So let's say this is my 0 and this is my 1. Okay, my rho could be anywhere between 0 and 1. It really doesn't matter. So let's say this is where my rho is. So that means I could make my epsilons such that, it falls between rho and 1. And that is possible because by adjusting this n. If the n is large enough, the epsilon is going to be smaller and smaller and smaller. In that case, it is bound to be between rho and 1. So let's say this is somewhere here, okay? There's rho plus epsilon. And let's call this R. Okay, so I'm going to call this R. So in essence, what I could say, absolute value of A sub n plus 1 is going to be less than R times absolute value of A sub n. Remember, this relation is going to hold true so long your subscripts are bigger than or equal to capital M. Now, this is, by the way, just for one term. I could extend it to the next term. Nobody is stopping me, right? So I could say absolute value of A sub n plus 2, right, is going to be less than R times absolute value of A sub n plus 1, right? But A sub n plus 1 is this, so I could replace, I could hold this relation R times R times absolute value of A sub n, right? Which is the same as R square times absolute value of A sub n. So in essence, I just showed that absolute value of A sub n plus 2 is less than R square times absolute value of A sub n. Similarly, I could extend this idea, absolute value of A sub n plus, let's say, some little m, okay, is going to be less than R to the power m times absolute value of A sub n. Now, this is the relation that I'm going to be using very shortly. And before I go into details of this, let me just remind you that this R is actually less than 1, a fact which is going to be very important for us. Now, let's go ahead and continue our journey here. So let's take the summation n is equal to 0 to infinity absolute value of A sub n, right? I'm going to break it down into two pieces. Summation n is equal to 0 to n minus 1 absolute value of A sub n plus summation n is equal to capital N, okay, capital N to infinity absolute value of A sub n. Now, I'm going to do a little bit of subscript manipulation. So let's say in this one, I'm going to replace n by m plus n, okay? That's what I'm going to do. If I do that, I'm going to get the following. So I'm just going to write this thing only. So it's going to be summation m is equal to 0 to infinity, okay, absolute value of A sub, I'm replacing n by m plus n. So absolute value of A sub m plus n. That's what it's going to be. So this becomes summation n is equal to 0 to n minus 1 absolute value of A sub n plus summation m is equal to 0 to infinity. So now I have done the shifting here, okay, shifting of indices. So absolute value of A sub m plus n. Now, here is the key part that you want to pay attention to. So this absolute value of A sub n plus m, which is the same thing as this, is strictly less than R to the power m plus absolute value of A sub capital N, okay? If that is the case, I could just replace this value by this, which is going to make it an inequality of this format, okay? So which is going to be less than, to be precise, but I'll make it less than or equal to. We are still good, right? Summation n is equal to 0 to n minus 1 absolute value of A sub n plus summation m is equal to 0 to infinity, okay, R to the power m times absolute value of A sub n, okay? So this is fixed from now on. So that's the key understanding here. Now, notice that this is nothing but geometric series. with r being less than 1. Okay? A sub n is fixed, right? A sub capital N is fixed number. So r less than 1, so this must converge, okay? And this is nothing but a collection of finite number of finite terms. That is also gonna converge, right? So together they're gonna converge, they're gonna be equal to some fixed number, okay? And let's call this k. So if you look at it, where we started here, all these things are equal as you go, equal here, and then finally we have gotten an inequality here. So that tells you that this series summation n is equal to 0 to infinity, absolute value of a sub n is less than or equal to some number. Or you can think of it as less than or equal to another series, because if you combine them you get another series, and it's a fixed number, it converges both of them. So by the comparison test, we can say that this series converges. So this is very important, okay, for you to understand this logical derivation. So we just showed the first case. Now let's go ahead and work on the case 2, which is rather easy. So first case is the kind of difficult one. So the case 2 is pretty straightforward. Absolute value of a sub n plus 1 over a sub n, okay, is greater than 1, okay. So now for some capital N, we could say if n is greater than or equal to, this is always gonna be a sub n plus 1, okay, absolute value of it divided by absolute value of a sub n is going to be greater than 1, or a sub n plus 1 absolute value is greater than a sub n absolute value, okay. Now this is kind of disturbing in a way. Why? Because as n approaches infinity, what happens? The individual terms, they do not go to 0, because it's actually increasing rather, okay? It's increasing. So that tells you that limit n approaches infinity, a sub n is not equal to 0. By the way, if that is the case, then the series obviously does not converge. Remember, if a series converges, then the individual terms must have to go to 0. And the converse of that statement is that if the individual terms do not go to 0, then the series does not converge. So that's very important. Here the individual terms do not go to 0. It keeps increasing, and we are dealing with absolute value, right? It could literally go anywhere, right, towards infinity. So if the ratio is greater than 1, okay, that means if rho is greater than 1, then it diverges. And of course, if this ratio goes to infinity, it's going to diverge anyway. And the case 3, so case 3 is pretty easy to show. You have rho is equal to 1. Consider the harmonic series summation n is equal to 1 to infinity 1 over n, and consider summation n is equal to 1 to infinity 1 over n square. Both of these series, consider them. Now look, if you take the ratio of this thing, what's going to happen? So let's find the limit n approaches infinity, okay, 1 over n plus 1 divided by 1 over n. And I can take the absolute value of it, but it's positive number, so I don't need to worry. That's going to be is equal to limit n approaches infinity. If I simplify it and divide both top and the bottom by n, I'm going to get 1 over 1 plus 1 over n, and that's obviously going to be equal to 1. However, we do know that the harmonic series diverges. So I have the absolute value limit of a sub n plus 1 over a sub n, absolute value of it, if I take the limit of it, I get 1. However, this guy diverges, right? The harmonic series. Now let's go ahead and do the same thing for the other one. So I have written it out here for you. Limit n approaches infinity. I avoided the absolute value sign because we are dealing with squares here and positive numbers, so nothing to worry there. So limit of n approaches infinity, 1 over n plus 1 whole square divided by 1 over n square. And if I simplify it, I get this, and then I divide both sides, both top and the bottom, the numerator and the denominator by 1. I get 1 over 1 plus 1 over n whole square. And as n goes to infinity, this obviously goes to 1. So, but we do know that summation n is equal to 1 to infinity, 1 over n square, that converges. So we've got two situations, two examples. Both of them have rho is equal to 1, but one of them converges, which is this one, but the other one diverges, which is the harmonic series. So that basically tells us the third condition. So that's how you show that the ratio test works. This is the proof. I hope that this discussion was helpful. Thank you very much.